Hello, in this video we are going to look at a biochemical redox reaction. So I have here the oxidation of FADH2 by ubiquinone, also known as Q, so that FADH2 becomes FAD and Q becomes QH2. This is the loss of 2 electrons by FADH2 and 2 protons. Up here I have the reduction potential for both of them, and you can see here's the standard voltage for each one of them. Now, because this is positive, it is going to want to be reduced more likely than FADH2 will. So FADH2 is happy to give up its electrons to a more positive voltage. So that's why we expect this to be spontaneous. So the question is, using these concentrations, what is the Gibbs free energy for this? But before we can do this under non-standard conditions, we need to first do it under standard conditions. So we'll calculate that using this equation, delta G naught equals negative NF delta E naught. We need to calculate the change in voltage under standard conditions, and in order to do that, we're going to take these two numbers up here, the standard reduction potentials, and put them in their appropriate location in the formula. Because Q is being reduced, I'm going to put it first, and FADH2 is getting oxidized, so I'm going to put it second. I'm not going to change any signs up here. I'm just going to put those numbers where they belong. The reduction, the species being reduced goes here, species being oxidized goes here. So it's 0.04 volts minus negative 0.22 volts. Which of course is going to yield a positive 0.26 volts. So if it's positive, that means it is going to be spontaneous under standard conditions. When we put this into the delta G, what we end up with is negative N is going to be 2. N represents the number of electrons being transferred, and we know that FADH2 carries 2 electrons, and so it will donate those 2 to Q. And then Faraday's constant, 96.48. Units on this are kilojoules per mole volt. And finally, our voltage, 0.26 volts. And then this is going to end up being negative 50.17 kilojoules per mole. So that is certainly very spontaneous under standard conditions. So now the question is, what about under non-standard conditions? So in order to do this, we need to use a different formula, very similar to the delta G under non-standard conditions. Here we have delta E equals the standard change in voltage minus this term RT over NF times the natural log of Q, Q being the same, products over reactants. Now you can actually reduce this term RT over F to be 0.0267 over, and then that of course is over N, the number of electrons, at 310 Kelvin. It's actually pretty much the same thing at 298 Kelvin. It doesn't change this value very much. So we need to find what our Q is. And Q is going to be products over reactants. So I need to convert these to molarity. This is my concentration of QH2. which is one of my products. FAD is also another product. And then Q and FADH2 are both reactants. So 0.05 times 10 to the negative third, then 0.2 times 10 to the negative third. That's our products, divided by reactants. 5e to the negative third, which is our FADH2 concentration, and then 0.1 e to the negative third, which is our Q concentration. Okay, so here's our Q term. And then we're just going to put that natural log of that value and then multiply it by our term here, 0.0267 over n. Our n here again is 2. And then we take the natural log of 0.02. And then over here we are subtracting that term from our standard change in voltage, which we found to be 0.26 volts. So when we do all of this calculation, should end up with a number negative 59.8. I'm sorry, that would be the delta G. This is going to be 0.31, positive 0.31 volts. And then when this is put back into the negative NF delta E equation, of course this is to 96.48 kilojoules per mole volt, and then our delta E, which now is 0.31 volts. This then gives you the negative 59.8 kilojoules per mole. So it's actually more spontaneous under non-standard conditions than under standard conditions. All right, hope that was helpful. See you next time.